Hello, my name is Stuart Beveridge and welcome to NACAA 2022. I am the NACAA 2022 Local Organising Committee convener and I'm coming to you from Melbourne, Australia, and I will be your chairperson for the day. The term NACAA stands for the National Australian Convention of Amateur Astronomers. NACAA conventions run every 2 years. The Astronomical Society of Victoria, or the ASV, of which I'm a member, was successful in their bid to run the 2022 NACAA convention in their centenary year. And this event will be the first time NACAA has been run online. The convention will be run over 2 days, with day 1 being today, April the 16th, and day 2 being on April the 23rd, which is the following Saturday. The presentations are broken into 4 streams per day, and you can have a look at any time at the program if you go into NACAA, www.nacaa.org.au/2022/program. So our first speaker of the day will be David O'Driscoll. David is the NACAA General Secretary and is a member of the Astronomical Association of Queensland and Variable Stars South. David is going to present Welcome to NACAA. You have the floor, David.
Thank you, Stuart. And welcome to everybody who's joined us online today, and also to those of you who may be viewing this recording later, as it will be recorded and available in perpetuity. As Stuart said, my name's David O'Driscoll and I'm General Secretary for NACAA, which is to say I'm the chair of the Secretariat, one of the 3 committees that run NACAA, along with the Local Organising Committee, for which Stuart's the convener, and the Program Committee, who have organised all our speakers today. I'd like to begin by acknowledging the traditional custodians of country throughout Australia and recognise their continuing connection to land, waters and culture. Observing and interpreting the night skies is a significant part of most Aboriginal language groups and has been used for navigation, calendars, ceremony, predicting weather, cultural law, songlines and art for thousands of years. I'm speaking to you from Brisbane, where the Turrbal and Yagara people are the traditional custodians, and I'd like to pay my respects to elders past and present. Today is the start of a truly extraordinary convention for NACAA for 3 reasons. First, this is the 30th NACAA convention since it commenced in 1967. And for those of you doing the math, it wasn't always held every 2 years. So the math doesn't quite work out, but it's certainly a truly notable achievement for an entirely volunteer organised event, especially when the event is only held biennially. Secondly, as Stuart's already mentioned, our hosts, the Astronomical Society of Victoria, are celebrating their centenary this year. That is yet another amazing achievement. And finally, this is the first time a NACAA convention has been held in a virtual format. While all involved would have preferred a face-to-face event, in the depths of the Omicron outbreaks across the country over the Christmas period, and to which I've recently succumbed, the Secretariat and Local Organising Committee felt that going virtual was the only way to allow us to continue the event. We didn't want to have to cancel it as we did 2 years ago. However, ASV have marshalled a skilled group of individuals to allow this to occur. And I'd like to particularly thank ASV President Chris Rudge, Vice President Mark Ascaro, and NACAA convener Stuart Beveridge for their work. Bringing this together. Mark, you can edit that out later. Mark is in fact the technical genius behind today's technology and deserves special thanks. We have an interesting program set up for today and for next Saturday, and hope you will enjoy this virtual NACAA event. At this stage, I'll hand back over to Stuart, our host for this morning. Over to you, Stuart. Thank you.
Thanks very much, David, for that great talk. And next on our program is our second speaker of the day, Mr. Chris Rudge. Chris is the President of the Astronomical Society of Victoria and will present his introduction from the ASV. Go ahead, Chris.
Good morning. On behalf of the ASV, I would like to welcome you all to the 30th NACAA 2022. We were given this conference, as previously stated, because we're celebrating our centenary. The initial planning was done as we were coming out of the COVID lockdowns. Then, as plans developed, it was obvious that few really wanted to travel. The ASV during lockdowns have developed the expertise using the internet effectively, first with Zoom and then the platform we're using today, StreamYard. We convinced the NACAA committee that we should run this year's conference entirely online. I think there was a great reluctance to travel with the difficulties, and we had difficulties finding a suitable venue. Looking at the way the airlines are today, I think we can all breathe a big sigh of relief that we're not travelling. The one thing that we will miss out this year, of course, is a chance to catch up with old friends and acquaintances, the chance of making new contacts. That's an important part of any conference, but unfortunately we'll be missing this time. The one big difference we've noted this year with several of our societies is the ability to gain grants. We obtained a small grant for an All Abilities Observatory and Telescope, Tamworth a larger one, and Port Macquarie an enormous one. It will advance the quality of our amateur astronomy quicker than anything else we can do. It's important that we all gather contacts and try and get grants for what we do. As I've said before, the ASV is proudly celebrating our centenary, starting off with a handful of enthusiasts in 1922 to a large statewide organisation today. We have almost 1,800 members, including a few overseas. This is all made possible using the Zoom platform, so that they can join in for most of our section meetings. Zoom has made it possible for members across the state to join in. One of our latest innovations is to start sub-branches across the state. The first was an amalgamation with the Bendigo District Astronomical Society, now known as ASV Bendigo. A group of enthusiasts have started ASV Shepparton, and ASV Heathcote, close to the Leon Mao Dark Sky site, was really a no-brainer. There are other groups that are forming across the state. Our big event this year, which is what we got the grant for, has been the opening of our All Abilities Observatory at the Leon Mao Dark Sky site. We had previously built a disabled toilet and shower. So to give proper access to the site for wheelchairs, we had to upgrade the site with asphalt paths lit with red marker lights. These go across much of the site now. People in wheelchairs do not have much control over their body temperature, as we do, fully mobile people. So we included in our observatory a warm room to shelter from the cold night air. This room will also form the basis for the visually impaired to look at the night sky, using, at least initially, monitors with the contrast turned way up. We've also been experimenting with tactile star maps, which are 3D printed, and raised print star maps, similar to the raised print of Braille. Our telescope for this All Abilities Observatory was designed, and a new hyperboloid secondary mirror was ground and figured by Barry Adcock, I think a familiar name to most of you. AstroWorks Diego Canello modified a Hubble Optics Ultralight 16 to the Naismith design. It was a great team effort to finish this project from many members of the ASV. It is an achievement that we can all be proud of. I think the defining moment for me was when one of our members, who is severely limited with his mobility, actually saw the telescope. The smile on his face made 3 years of hard work worthwhile? Well, the next 100 years put the ASV and our amateur astronomer community. I sincerely hope that we'll come out of our society's silos and look to a similar overarching organisation such as the BAA here in Australia. This will give us clout to approach politicians for serious grant funding to advance our astronomical goals. Tourism, perhaps even small CubeSats with telescopes above the clouds, the bane of all amateur astronomers. Whatever happens, it will be done by teams of dedicated enthusiasts. There isn't room really for ego. We need to unite as a team and we will get far more done. That's my introduction. Please enjoy NACAA 2022 in its new format. Thank you, Stuart.
Thank you very much. Thank you very much for that, Chris. Our first presenter for the day will be Dr. Sara Webb, and she is going to present the keynote address. Sara is a current postdoctoral researcher at Swinburne University of Technology, and her research has focused on observational transient astronomy, fueling her fascination for the unknown. Sara works with thousands of images of the night sky taken only seconds apart to measure the brightness of stars, galaxies, and even cosmic explosions. So across to you, Sara, you have the floor.
Awesome. Good morning, everyone. Thank you for having me. I will switch to my PowerPoint now. So I'm so excited to be here and to just chat about my favorite thing, which is just astronomy in general and how anyone, anywhere nowadays can get involved, which all of you know all too well how lucky we are to live in the 21st century where we have access to silly amounts of data and affordable telescopes compared to the good old days. So I hope to take you on a bit of an adventure and hopefully intrigue you with some of the most mysterious questions that we have in the universe. And I look forward to answering your questions as well. So before I get started, I would like to make acknowledgement of country. So where I work and where I live, I respectfully acknowledge the Wurundjeri people of the Kulin Nation and pay my respects to their elders past, present and emerging. So this beautiful, lovely picture of the night sky, this was our universe until about 100 years ago. All of a sudden, when you looked up at the night sky for many, many thousands of years across civilization, this is what we saw. And this is so important to us as humans. We were able to tell stories and communicate through the stars, use them to travel vast amounts of distances and explore the entire world as we know it. However, when we looked up, that was our universe. We didn't really know what was out there. We didn't know that we ourselves were a galaxy, that there were many, many others. And even though this great sky that we can look up at with our own eyes is vast enough and magical enough, it got even larger and even more magical in 1925 with some observations from Hubble. So before Hubble came along, this is what our observations looked like. These are some of my favorite things from the Messier catalogues, the original hand sketches of what they were seeing through the telescope. Before we had great photographic plates to be able to take long exposure images, the best we could do was to translate what we saw with our eyes down on paper, which, as you can appreciate, is probably incredibly difficult. And I myself absolutely would not have the artistic skill to be able to articulate what I saw down on paper. So it is amazing that astronomers for hundreds of years have been trying to understand the awe of what we were seeing up close by trying to convey it. And it was quite difficult to do this and took a lot of time and a lot of resources. We then entered, I like to call them this, like the golden years of original astronomy, where all of a sudden reflector telescopes were becoming more available. We started to understand how to use spectra. So how can we split the light from the stars that we're seeing and try figure out what is in these stars? So Maria Mitchell and Henrietta Labbett did an incredible work of figuring out the composition of stars. And then, of course, Hertzsprung was able to then figure out what is this kind of family tree of stars that we see. We obviously, to our eyes in the night sky, they all look pretty much the same size. Maybe some are brighter, some are dimmer than the other. But we now understand via spectra and observations and distance calculation that the amount of stars that are out in our galaxy alone that we can see is vast, and absolutely not all of them are like our sun by any means. And so this early age of the 1900s, all of a sudden we not only could see our universe, record it, but we could try to understand it a little bit better. And of course, Hubble comes along. Edwin Hubble was a pioneer at being able to take these newly analyzed stars, so a lot of work from Henrietta Leavitt, to understand that some stars were variable, and they were variable on periodic timescales, which meant that we could try use them to track distances. So, sorry, just waiting for a truck to pass. So Hubble was able to take this work that the previous scientists had built upon in understanding exactly what are stars and use them to try calculate distances. Because in the Messier catalogue, we saw that there is an incredible amount of nebulae and what we now know are galaxies. But back in the day, we thought that maybe they were all part of this one surrounding universe that we considered. And it was Hubble's work that showed us that our universe is extraordinarily much bigger than we thought, and all of a sudden a lot of these nebula were actually galaxies very, very distant to our own. And so all of a sudden there's a lot more space for us to explore and understand. So the 1930s of astronomy was an incredibly exciting time. We're starting to figure out some of the mysteries of the universe and kind of understand where our home is in this universe. So to highlight astronomy in the past, we go from using handheld telescopes that were fairly easy to use to all of a sudden we needed bigger and better instrumentation. And this is where some of the original large-scale telescopes come along. So I've got one of the Dunlap telescope, which if you're ever in Canada near Toronto, you can go do a tour of the Dunlap Institute. And the facility is just incredible. That this was one of the largest telescopes at the time, and the engineering that goes into just being able to move a telescope to track the night sky. I think we take it for granted these days when we can just hit a button and track whatever star we would like. Back in the day, it required an insane amount of beautiful engineering on very large scales to do. Then I also have an image here of the Hooker telescope. So these counterweight systems that allowed us to use large telescopes and to track the sky were just incredible. And one of my favorite things about these original type of telescopes, we've got to remember all of them were now using glass plates that you slid into the telescope. An observer, an astronomer, had to be at this telescope all throughout the night, sitting there, making sure that their plate was being observed properly. And you can imagine very, very dark, very, very cold. It would have been a long slog to get the data that we have. And this is what the data would have looked like back in the day. So I'm sure you're all very familiar and appreciate the art of these photographic plates. But what is incredible to me is just how long of an exposure you needed to have to get anything as detailed as these photographic plates. Many, many, many hours worth of exposing to be able to have this detail. And so you can probably appreciate, couldn't survey large amounts of sky, had to be very specific with where we were looking and targeting to try explore things. So it was a long, tedious job. But with this, again, just our universe was opening up on an insane scale, that not only are we detecting galaxies, but we're starting to see that the universe looks like it's expanding. We're starting to understand that there's explosions out there in the universe that we can detect. It's a pretty amazing and awesome time. So I'm going to jump ahead now about 70 years to where we are right now, astronomy in the future. So a lot has happened in a relatively short amount of time. So in less than 100 years, we've gone from using handheld or photographic plate telescopes and spending a lot of time trying to get our images to all of a sudden we have an insane amount of incredible robotic automated massive field of view telescopes and telescope surveys. And just for comparison here, this image has an image of the full moon and an image of Andromeda overlaid on these CCD arrays for the different telescopes. And they're very huge. They're amazing. So the amount of data we can capture, especially now with CCDs, it's mind-blowing, and it's incredible. And every night we are imaging thousands and thousands of square degrees of sky. So what I think is important and not a lot of people know is that most professional astronomical data is made public eventually. So most of it, you have a proprietary period for about a year where whoever the scientists were that gather it can do some analysis, and then after that it is online for free, completely accessible by anybody. And so I'm going to send some notes out to the organizers after the conference to send around to you with some links on where to get this data, because I'm sure some of you are probably interested in having a play around. And it's amazing. And even as an astronomer, there is so much data that has been collected that has not yet been touched or analyzed in the way that it should. So we're kind of entering this era now where we're getting more data than our eyes and our hands can handle. And this is very exciting because we're entering a world of using machine learning to help us discover what is interesting. But again, that takes a lot of effort and a lot of manpower, which I will introduce you all to in a moment, and how we can all help contribute to our understanding of the universe. So, and of course, we have these large professional astronomy surveys, but we live in a time where we can go and grab a pretty affordable telescope that automatically tracks for us. We don't need to do anything crazy difficult, and take the most spectacular images and data of the night sky that if you were to show that back to Hubble back in 1930, he probably would have fallen off his chair at how incredible these telescopes are. And you would all be more familiar with these type of telescopes than I am. I only get to use them occasionally, but it is so rewarding to be able to use something physically in your hands and see with your eyes the outcome. As an astronomer that works with these large survey data, I don't get to do that. I don't get to I just get the images after they come off the telescope. I don't get that wonder anymore. And I think that wonder of being able to observe yourself is some of the most important experiences that anyone can have in their life. Because I think it really opens you up to just appreciating the world, the universe that we live in. So yes, we're all incredibly lucky and very, very thankful to the organizations like ASV that we have here in Victoria that open this up to the public. So the coolest thing about this is now we live on a globe. Contrary to some belief, we do live on a lovely, lovely globe, and we have the access of the internet, which is pretty spectacular, which means that we can communicate with anyone, anytime around the world, which means that we can grab data from anyone, anytime around the world. We can help each other. We can explore the universe together, which is pretty amazing. So I wanted to try break down some of my favorite big questions that we have in astronomy today. So there are some pretty big questions in modern astronomy and modern astrophysics, and I will do my best to briefly introduce them to you, but I welcome any questions about them. I can go more in detail for any specific questions, and I would love to. So I've broken down our big questions in three different categories. So I've broken them down into physical systems, the universal recipe, and understanding ourselves. So with physical systems, this comes to our understanding of stars, galaxies themselves, and one of the big ones is explosion mechanisms. So I'll get to this a little bit later on, but the idea is that there are an insane amount of stars in the universe that are coming to the end of their lives, and many of which explode when they die. And understanding these explosion mechanisms and some of the physics that goes on, we can better understand how a lot of the matter and the elements that we need and use every day that are here on Earth have formed throughout the universe. We can even understand better how star systems form and interact with each other over time. It's really exciting, and there's a lot of things that we don't know yet. Another important area is changes over time. So you might have heard of the epoch of reionization in the universe, where all of a sudden everything got reionized. We wouldn't have the universe we have today if this didn't happen billions and billions of years ago. There's another problem that we call cosmic noon in star formation. So when we look back at very old galaxies, we can figure out how many stars are they forming based on a couple of different things. And what we find is that pretty quickly after the universe began, we had this rapid increase in star formation. And that's when a lot of the larger stars that would have then died and produced stars like our own formed. And it happened pretty quickly. And then we kind of see it peter down. And we don't know exactly why that happened so quickly. How did this process occur? And so trying to understand that is really important, and trying to understand how massive were galaxies when they were first forming after the Big Bang. And again, we're limited by how far back we can look back in time, how big our telescopes are. But things like the James Webb Space Telescope is going to help us immensely in trying to answer and understand these questions. Now I move on to universal recipe, and these are some of my favorite unsolved mysteries of the universe, and they're probably some of your favorite too. So the first one we have is dark matter. First of all, what is it? That is probably the biggest question, is what exactly is it? Is it detectable physically? And is it part of our understanding of the standard model of physics? So we are all made out of something called baryonic matter. Everything that we see and interpret in the universe is made out of baryons, and how they interact. However, dark matter, we think, interacts very, very, very weakly with any of this. And we're concerned, maybe a little excited, that it could be a completely different type of particle systems that we have yet to discover, because we are stuck interacting with our normal matter. So I think it's absolutely fascinating. I will touch on that more. But for now, let's jump to dark energy. So we have a theme in astronomy. We like calling things that we don't quite understand dark, because it's mysterious. It's hidden in the dark. Dark energy is this universal vacuum pressure that we are detecting that is making our universe not only expand but accelerate. Now, dark energy is a bit trickier compared to dark matter. So dark matter we think is a physical thing that theoretically, if we could interact with it, we could grab some, we could use it. Dark energy, on the other hand, we think is more a principle and a constant in space-time itself, which really hurts your brain to think about sometimes, but we live in the fabric of space and time. General relativity explains how matter bends space and time, but there's also a principle in general relativity that Einstein had put in called the universal constant, and it was a negative one. And this was to balance out the universe that Einstein thought we lived in, which was static and unchanging radially. However, we've now discovered that -1 actually works incredibly perfectly to describe dark energy and stabilizing the universe we live in mathematically. And so we think this dark energy is just a principle of space-time. So if you were to grab a box of space and time, it would already have dark energy inbuilt in its properties, and it would be expanding. Which really, it does blow your mind to think about. But some of the big questions we have about this is, does it remain constant? Because from what we understand right now, the pressure is constant all throughout time, all throughout the universe, or does it evolve over time? Now, this is very, very interesting, because if it evolves over time, or depending on where you are in space, this could mean that some parts of the universe, our very, very large universe, could be expanding, accelerating faster or slower than different parts. And this is a very interesting question that astronomers are trying to answer, is could that be true? And if so, what does that mean for the future of our universe? Finally, we get to understanding ourselves. This is, again, another one of my favorites, is trying to just place ourselves in the universe and understand Are we special? Is Earth one of a type, one of a kind? Did we just happen to have all of the right circumstances at all the right times and we got lucky and here we are? Or are there bazillions of Earths or Earth-like planets out there? Is there the possibility that life as complex as what we see here on Earth has formed elsewhere, which I think is absolutely fascinating, and just trying to understand star systems in general, because there's a lot going on out there. And of course, alien life. So we want to know, does it exist not only beyond Earth, but in our solar system? Because that would be pretty incredible and give us a lot of understanding for how the building blocks of life might have been distributed. So for life, we need amino acids. That is one of the key things to getting us going, to building RNA, eventually DNA. And we want to know, could those amino acids be distributed elsewhere? Because we do find them on asteroids. And does that mean that life, even basic, simple microbial life, does that form elsewhere in our solar system? Which I think in our lifetimes, we might get an answer to, because we've got some very, very exciting space probes and space missions that are heading out to the moons around Jupiter and Saturn. And these moons have subsurface oceans. And we know here on Earth that if you want to get the most life you'll ever see, you take a drop of water from the ocean, and the microbial life is incredible. And we think that life formed in this kind of primordial soup in our oceans. And so why couldn't it form on alien moons somewhere like that? So I think in the next 20 to 30 years, we might be able to have an answer of, is that a possibility or is it not, which is so, so exciting. And then finally, could intelligent life detect outside of our star system? And are we able to detect any signs of that? Because we have incredible technology now. Are we able to detect anything? So they are my three big umbrellas for the biggest mysteries of the universe currently, and in my opinion. And I'm going to take you on a bit of an adventure through each of them and how you can contribute to analyzing, using, and finding data that could help solve these mysteries. So first of all, let's start with explosion mechanisms. These are near and dear to my heart because a lot of my research is done on exploding stars or variable stars. So I quite enjoy these. So one of the main explosion mechanisms that happen in the universe is supernovae. And you're probably aware that they come in all different types of flavors. So they come in a heap of different types because stars are all different sizes, different compositions, so that we can explode different ways. So to break it down, we have something called a type 2 supernovae, which is basically a core collapse. These are our biggest stars in the universe and in the galaxy. They are immensely massive, at least 20 to hundreds of times the mass of our sun, much, much bigger. And they're able to chew through all of their hydrogen and helium much, much quicker than our sun. So they tend to have very short lives, but when they get to the end of their lives, they end it with a bang, because all of a sudden they start producing iron in the core, and that is unsustainable for fusion. All of a sudden you're not releasing any more energy, you're just consuming it, and these stars implode from the center and spew everything out. And these are amazing because about every second in the universe, a star is exploding somewhere. Every single second, which is incredible to think about. We then move on to a different type of exploding star. This is another one of my favorites because we can do a lot of science with them. This is called a type 1a supernovae. And these, instead of collapsing from their core, these are something we call thermonuclear runaway. So what that means is we have a star that is not massive by any means. These stars are very small. There's something called a white dwarf, and they tend to be about the mass of the sun, or slightly more, slightly less. They are the remnants of what our sun will eventually become. They're leftover stars like our sun. And in them, it's lots of carbon, lots of neutrons, and they're very, very dense. They're the leftovers of the fusion process. Now, what can happen is that these have to remain at a certain mass before they become unstable. So you might have heard of something called the Charleston Chandrasekhar limit, sorry, tongue-tied. The Chandrasekhar limit is 1.4 solar masses. Basically, what that means is that when you have a star of a certain radius, if you exceed that mass limit, they can basically ignite themselves and create an explosion process throughout the materials that they have. And these are great because we know this type of explosion only happens at that mass, whereas the other stars can explode at many, many different masses. These only explode at that mass. And we think to get this explosion to happen, we have to have pretty complicated star systems. We either have to have two of these white dwarfs, and one of them is excreting a bit of material from the other, or we have one white dwarf near a bigger star, and it's also stealing some material until it gets heavy enough. So these are super interesting, and I'll explain why we want to understand a bit more about these in a minute. But we also have type 1b and type 1c. Didn't want to leave them out. They're just core collapse that don't have as much helium in their spectra and other things like that. They have slightly different properties. But yes, the main thing that we want to know is we want to understand better how and when do these explode. So you might be asking, we have tens of thousands of these detected across the universe. Every night we're finding more. So what is the problem? We have lots of data. What more do we need to know? And one of the problems is shock waves and explosion breakouts. So these are pretty gnarly in the universe. So when you have a star that is either collapsing down in that core collapse or undergoing thermonuclear runaway, you have a shock wave occurring in the star. So for core collapse, I've got an image here. All of a sudden, it starts to explode. You've got a shock wave traveling through the material of the star. When it gets to the stellar surface, so we know that our sun has something called the corona, which is all of those incredibly hot, energetic particles, very, very, very hot. When this reaches that surface and then beyond into the corona, it ignites. It is, you can imagine it as the biggest firework you could ever imagine. It ignites for a short period of time before it fizzles away again and the rest of the explosion occurs. Now, understanding that can tell us a lot about the star's composition because it lights up a lot of different elements that then in spectra we can try understand and break down and figure out what are these stars made out of. We can also use this, there's a different type of shock breakout for those white dwarf scenarios I was talking about, for if the white dwarf explodes and it hits that companion star and lights up that star, we can then better understand what was that companion. Was it another white dwarf or was it a big giant red star? Because at the moment we don't know. We think that they're the possible cases, but we don't know for certain. So what is amazing is we've detected literally less than a handful of these shock breakouts that we call them, and some of them are still speculated. This is pretty much the only the only official one that's been confirmed. This is an incredible point of data. So we see here that the star is exploding and it kind of gets brighter over time, but you see this little zoomed in box here where we have this tiny little spike. That is where the shock breakout has occurred. And that's just one point of data that we have. And it happens in about a 30-minute period. So 30 minutes, that's all you've got to try and find these things. So incredibly difficult to find, but can tell us an immense amount of information. So trying to understand these is very, very important. So to understand these, we need to be able to detect when a star is going supernovae pretty quickly. And to do that, we need early detection and identification. And most of the time, we need to do that through machine learning because we can't have a poor human sitting at the computer night and day looking at data. They would never see all of the data, and it would be cruel on our astronomers. So we want to make the machines do it for us. So with data coming off telescopes so much quicker than ever before, literally within minutes, the data is off and being calibrated. We have the chance to then look at this data with machines, identify anything that could be a rising supernova and trigger other telescopes to look for those shock breakouts or other things. So this is some pretty awesome data that I've got here. We can see on the left-hand side, where it says quiet, we've got this little blip that has occurred in some data here. And this blip, you can barely see it. It's only a couple pixels. Really, we needed the machine to tell us that this was significant. Hinted at the fact that a star was coming to the end of its life. Hinted at the fact that there was a pre-explosion eruption. And through identifying this, they were able to monitor it and see that all of a sudden we had another blip, a largest pre-explosion, and then we get our supernovae many days later, which is pretty awesome, because through this time they could then monitor it and get some pretty amazing data. So this is just one example of that type of work working out lovely. So if you are interested in looking at these type of data, so those images where you're really trying to spot supernovae in the image, I'm going to talk about Zooniverse a bit, because I think it is one of the most incredible platforms that we have the privilege to have access to, not just for astronomy data, for all sorts of data too, but I'll keep it to astronomy for today. But it really does, it gives you real scientific data at your hands, and it gives you detailed instructions on what you're looking for and why, and you learn quite a bit. And I love doing these in the little free time I have. They are so relaxing and so much fun. And so the one that can contribute the best at the moment to trying to find supernovae is actually the Zwicky's Quirky Transient. So the Zwicky Transient Facility is run out of Caltech, and it is the next generation from the Polymer Transit Factory, which you might remember from a couple of decades ago. And it is immensely amazing at the amount of data they are getting. And so they want to build very, very complicated machine learning algorithms, but they need humans' help to try classify things. And that's where we can come in. So again, in my notes that I'll send around to the organizers to distribute online, I'll have a heap of links. But if you just Google Zwicky's Quirky Transients, it should come up. And that is a lot of fun. I highly recommend it. But if you want to get a little bit more in-depth and hands-on, you can try find supernova with your very own telescope. So I've got a link here to one of our guest contributions on the Swinburne website from Reverend Robin Evans, who actually won the Page Medal back in 1982. So his work is amazing. I think he still holds the record for the most number of supernova discovered by himself with his own telescope. And really, to discover supernova, all we're trying to do is you take a photo of the sky one night, you come back the next night or a few nights later, months later even, whatever time frame you would like, take another image of the same patch of sky, and then you subtract them. And you're looking for anything that got brighter or anything that got dimmer. And it's pretty simple. It's kind of like just 1 + 1 = 2, and we're just playing with images, which is pretty awesome. And this article outlines some of the awesome tools that you can use online, all of which are free. All of the tools that I use to do any of my analysis are all free online, which is the best thing about astronomy, is we like to have things open source and free. And so if you're keen to try catch a supernova by yourself, highly recommend having a read of this article, or even if you can, chatting to Robert. Okay, next up we have the dark universe. So again, the magic of our understanding exactly what is this universe we live in, because it's pretty mysterious. So let's first of all touch on dark matter, because it's pretty epic. So we think that 30% of the stuff in our universe is dark matter. So to put that in perspective, the 5% that we can see, experience, observe, and interact with is our matter, 5% of the energy density. Crazy. So 30% of this is something that we to date have not been able to detect. And it's very complicated because we know it has to exist. The evidence for dark matter is so unrefutable at the moment. So I've got an image here. This is something called a strong lens. And this would only be possible if there was obscene amounts of dark matter in the universe. So what is happening here is there is a very, very large galaxy cluster in the foreground, and it has a lot of dark matter and what we call halos around the galaxies around the galaxy cluster. It is so heavy on space and time. You can think of it as an adult jumping on a trampoline. It's bending space and time, and the light from behind is getting stretched along with space and time until the gravity lets up and it can travel freer again. So lens systems like this are a great way of us trying to understand that there's dark matter out there. We can also figure out that with galaxies and the way that they rotate around, they rotate much different than if they didn't have dark matter. So the edges of galaxies are rotating faster than we would expect if it was just the light that we can see. So it's pretty awesome. And we know that dark matter is absolutely vital for the way that our galaxies have formed and the way that matter has been distributed around the universe. So that simulation image previously, this is a simulation of what we call dark matter traces, halos and filaments in our universe. And when we observe galaxies and map them, this is what our galaxies look like. They're in this cosmic web looking structure. But for this to form, there has to be large amounts of dark matter clumped in certain areas. So it's pretty amazing, and we want to understand more. So for some citizen science, this is tricky because I would love if we could try to detect dark matter particles at home, but unfortunately those detectors, we're currently building one in Victoria called the Sabre detector. They need to be super far underground, very pure crystals to try to detect any interaction. So unfortunately we can't go that direct route, but what we can do is take either any data from online or your own data from telescopes and try model gravitational halos and see what is the lensing happening. This is a bit more involved because it does involve some Python programming and scripting, but there's an amazing package called, I think it's called Spaghetti Lens, that is free and available, and I've put the link here to read more from the author of it and then to download it if you're interested. And what this does is you can take an image of the night sky. So we've got one here, and they've zoomed into this little patch where it looks like there's a halo. So that red galaxy will be in the foreground closer to us, and those blue dots are actually one galaxy that's behind it that has been stretched, and the light is splitting, and it looks like we see four of them from this lens. And the software is able to tell us, hey, this is where the most of the dark matter would have to live for you to get this shape. Pretty awesome. So this is something that I would love to see someone play with one day and see the type of results we can get. Finally, we're going to move on to dark energy. So a little bit different again. So again, dark energy, not a tangible thing that we know of, so a little bit trickier. So we think it's a universal constant. We understand it and model it as this negative energy density pressure on the universe, so something pushing outwards on space and time. And it's completely responsible for our universe expanding and currently accelerating. So the reason our universe will continue to accelerate as we know it is, you can imagine at the very beginning of the universe, if you have one square, and you have some matter in there, some radiation, and some dark energy. So the dark energy wants to push outwards constantly, no matter where it is. So it pushes that square, and some of the matter falls out of that square. So now if you measure that square, you've got less matter, and the dark energy is able to push easier. And this just keeps happening. So for each measurement of space and time that you want to make, matter keeps moving away from each other. And then the influence of dark energy on the current matter that's in that square is greater. And it just continues. From what we understand, it will just continue forever from what we understand. But we do want to understand it better and see, is it changing, and what other amazing things can it tell us about our universe? So the best way to understand dark energy is to map our universe, to map how far galaxies are away from each other. And the brilliant thing about light is that we are restricted to how fast it can travel, which means that when we're looking back at distant galaxies, we are seeing back in time. So we are getting snapshots of our universe through the ages. And that's very helpful because then we can map how fast it was accelerating through those ages. So we use type 1a supernovae to try and map distances to galaxies, But there's another method that's really interesting. So this is actually trying to just locate very, very, very distant galaxies to try build up our understanding of the cosmic web at that epoch. And so this is another Zooniverse project called the Dark Energy Explorers. And in my opinion, this is one of the coolest you will probably ever do, because you are looking at data that no one else has ever looked at most of the time. No other eyes have seen it apart from you and the other people on Zooniverse who are looking at it. And the data is of galaxies that are 9 to 10 billion years old. So an incredible amount of space and time has passed since these galaxies were even forming. It's pretty amazing that light is that old, older than the age of our sun. Incredible. So I highly recommend checking this out and seeing if it's something you might be interested in. From what I had to play around and doing it myself, I thought it was very neat and like data that I had never seen before. So very, very cool. Finally, our last big topic is Earth special? And in my biased opinion, I think Earth is incredibly special. The fact that we exist and are intelligent enough to come together and meet and discuss about the universe together, understand science as we know it together, I think is very, very impressive of the universe. Good job for making us. But we do want to understand, is this world that we experience with the beautiful amounts of biodiversity, insane amounts of different types of life, is this common, or did we just hit the jackpot universally? So to do that, we kind of want to understand where around stars could a planet like Earth form. And really, when we break down the most important thing for any organism on Earth, it is water. We need liquid water. And the reason that water is so important to us as humans is it helps facilitate, or us as living things, not just as humans, anything living, helps facilitate different chemical reactions that happen that we need to have our body do what they do. And so we really do need liquid water for life as we know it. And what we have is something called habitable zones around stars. So this is where at a certain zone, it's not too hot, not too cold. You can call it the Goldilocks zone. And water can form in all three states. So liquid, gas, and then also it can be ice as well, depending on the type of planet you live on. And we think this is very important, but it changes depending on what type of star you happen to live around. So we live around something called a G-dwarf star. Our lovely sun is the mass that it is, but it's actually quite small compared to other stars, and it's in the middle of its age. So it is this nice compact star. However, our star will get bigger as it gets older and expands its gas. And so we have here what our old sun will look like in many years' time, nothing for us to worry about. But when it does become a red dwarf, its radius increases dramatically, and all of a sudden that habitable zone where liquid water can form is nowhere near Earth anymore. We are burning up, if not within the sun, and Jupiter and Saturn now are the places where water could be liquid. So this is important to understand because it means that where life could exist changes over time, changes depending on the type of star, and changes depending on the age of that star. So before we can even understand the habitable zones of other planets, we need to find them first. And thankfully for us, we've gotten really good at finding exoplanets. Just last month, I believe we confirmed our 6,000th exoplanet, which is spectacular considering I think the first one we detected was in 1992. So about 30 years, and we've discovered 6,000 of them, and many thousands more to be confirmed. So it's incredible, and really the principle of how we detect exoplanets is quite simple. The majority of the way that we do it is something called the transit method. And so if anyone has been lucky enough to view the transit of Venus or Mercury in front of the sun in the past decades, it's awesome when you look at it either through a telescope or through it reflected on paper or through special glasses. You visibly see that the planet goes in front of the star, and that little patch where the planet is, it gets darker because it's blocking out any of the light from the star. So we use this same principle for how we watch transits of our planets to try find other planets, because all of the other stars we can look around and see if we can detect this continual dimming in brightness, and is it periodic, and if it is, we can do some modeling to then figure out what type of planet might be around it. And this is pretty easy because all you need really is images and good quality systematic analysis. So we need to be able to say whether the dip was significant or not, but most of the time the dips in the brightness are so much further than any of the error bars that we have on our detections that they are undisputably real. So pretty easy, something that we've mastered the art of doing now with our various different telescopes, and many of which are in space, but the program I want to talk about is actually something here on the ground. So this is called Planet Hunters, and it's from a survey called the Next Generation Transient Survey. And they are pretty awesome. They're using robotic telescopes to take very quick images of the night sky, something similar to what my previous work is doing. And they're trying to understand just stars in general. So variability of stars, the flareability of stars, and also the planets that exist around stars. So in this project, you are looking at those light curves over time and looking for that lovely dip to try identify if there's a star or not. And they've got multiple levels to this citizen science project where you can then do some secondary analysis to further confirm if we think it's a planet or not. It's really, really cool. And I think the best way at the moment to get a hands-on approach to trying to find a planet for yourself, which is really, really awesome. So with that, I hope that I have summed up a good chunk of some of the universe, but I know you will have lots of questions, so I've left a good amount of time for you to please ask your questions. Depending on where you're watching and where the platform is where the questions can be asked. I think if you're on YouTube or Facebook, you just type them in and we can see them, and I will pass it back over to Stuart to field questions.
Thanks very much, Sarah. That was a great talk, and we've had quite a few questions coming in, and I'll just go and have a look at the first one. So I'll start with David. David, hang on, is that the right one? Here we go. As amateur astronomers and citizen scientists, where do we best direct our efforts? Our own observations or analysis of data from professional programs?
This is a really good question. So I think it depends on what you want to get out of your involvement in astronomy, because I think both are very, very important. So I think being able to do your own observations and learn and understand the universe teaches you so many things that many of these online like Zooniverse programs, you wouldn't get to experience the things that you learn doing your own observations. But I think the best way to contribute to the overall understanding of science is helping through these like citizen science outreach efforts, because we do not have enough astronomers to handle the data that we get. And so we're trying to think of clever ways on how do we share that data without having to bore everyone to death with the boring things behind the analysis and the collection, because I can promise you some of it is so tedious and not interesting and not magical. But we want to be able to not only educate through these type of programs, but also inspire and then do some great science. So I think both are very, very valuable. And I think there is definitely not a right answer, because anything you're doing is helping progress both your own knowledge, which is just immensely important as a human, is our understanding for the universe, and any of these online citizen science programs, or even observing with other programs, say following up if there's a supernova nearby that you can get data of. That's brilliant. That is also assisting. So Yeah, great question.
All right, I'm just scanning here. There doesn't seem to be a lot of questions.
Feel free to ask you can ask big questions about dark matter, dark energy, anything like that I might have not been able to clarify in the brief talk. Any questions that you have, generally just as the curious humans that you are about our universe, and I will do my best to try answer.
Yeah, no, I think everyone's enjoyed your talk so much. There's not very many questions, but
That's very kind.
what is the latest though, Sarah, on dark energy? What programs are currently running now, and what is the understanding of that between dark energy and dark matter? What's the difference?
Yeah, so I missed at the very beginning of that question, but just to recap, what are the main differences between dark energy and dark matter themselves, and then how we explore for them?
Yes.
I think with that, yes, sorry. Okay, yeah, so really good question. And I think the best way to think about it is dark matter, we think is physically something just like us. So we're a clumping of atoms and particles. We think that dark matter is another type of atom that exists. And we know from our observations of the way that light bends is that dark matter exists in these big clumpy halos around galaxies. So you can almost imagine a galaxy forms in the middle of a dark matter bubble. Because it's nice and heavy, things can clump together easily, gravity can take control and create the galaxies that we see. What we don't think dark matter does is move very quickly. We know that it's moving continuously, but it's not traveling. It's not traveling like the speed of light or anything like that. It's kind of pretty stationary, like most other particles. So the way that dark matter, we are trying to detect dark matter is we are assuming, just using a hypothesis, that it hopefully will interact with our type of matter occasionally, very, very weakly. We think that it might interact. We can kind of compare it to something similar to when we are trying to detect neutrinos. We know neutrinos are part of our standard model, and we're able to detect and produce them easily enough. However, they don't interact with things very often. So right now, just sitting here, all of you have hundreds of trillions of neutrinos passing through your body constantly, because we exist near a star that is producing a lot of them. However, they pass through, they pretty much will not interact with any of your atoms for the most of your life. And so we try to detect neutrinos by making them interact with stuff. And we're going to try to do the same thing with dark matter. We're going to try and make it interact with very dense, perfectly structured crystals, because when they do, they should knock off an electron that will produce light that we can detect in these detectors. So very, very tricky. With dark energy, on the other hand, we almost are kind of thinking or at the consensus that it's probably something that is only detectable through its actions. So we can understand that the universe is accelerating, is moving and expanding, but we don't think we can detect dark energy like a particle. We think that it's a constant in the universe, which blows your mind that our universe has so many constants in it to make it the universe that we are. But we don't think we can physically detect it or hold it. But we do think that we can measure it very well. And the way that we try and measure it is a couple of different ways. So we try to model so Einstein's general relativity, we try to model that universal constant, the negative one that he put in cheekily to stabilize the equation. And so what we do is we solve for those equations using our data that we have and try it. You can think of it as like rearranging an equation basically and trying to solve for x. We're trying to do that with lots of data. And when we solve for our x or that omega, it ends up being very, very close to that negative one. So that's how we measure it with a universal constant.
Yes, which leads to another question from Bill Hatzavaris. Is there a unit of measure for dark energy? I think you just...
Yeah, great question. So not so much a unit. We think that we measure the way that matter and energy interact with the universe on pressure scales. So you might hear something called an energy density pressure. And so we measure dark energy to have a continuous energy density pressure across the universe, whereas matter is declining, and radiation is also declining. So not so much a unit, not anything fun that we can call it, but we try and measure it in pressure.
Just another question, while we're still on the topic, do we still think dark matter, this is from Doug Stenhouse, do we still think dark matter is a particle phenomenon? If so, how would it fit into the standard model, or could it be something else entirely?
Yeah, that's a really great question. So we think there's lots of different schools of thought, and nobody is right, nobody is wrong, because we're yet to have enough evidence and data to confirm anything. But we're thinking that most likely it's a particle. It's most likely a particle that is very small, very cold. So what that means is it moves slowly and it doesn't interact a lot. So we're leaning towards it. It could be part of our standard model and just something that is so weakly interacting with the rest of our standard model that we have yet to be able to understand it, or that it maybe be not a separate standard model, but it could be something else entirely. It could be another level of our understanding of particles. Maybe we are just touching the surface with our understanding of what we can do today. And there could be a whole nother hidden layer of other particles. So it could either be one type of particle or a few types of particles in a different model. But in saying that, there's other theories to say that dark matter, you might have heard of things called machos, or massive, I forget what the term stands for, but basically big clumps of something heavy. And one idea is that there could be a lot of very tiny black holes everywhere, primordial black holes, and then other types of very tiny black holes. However, with this theory, the amount that you would need to make the dark matter amount that we see around massive galaxies is an obscene number of black holes, a lot. And we would think that we would be able to detect them, because if these black holes, these small black holes exist, they're moving around, and when they pass in front of stars, it should lens the light. So similar to how we see big gravitational lenses around galaxies, if a black hole passes in front of a star, it will also lens the light, and that star will get a bit brighter for a period of time. However, we do not find them yet. There's projects they're working on trying to see, is there other types of black holes that we haven't detected yet? But I think most people would be willing to bet a coffee or bet a beer that it's probably a particle type of situation. But who's to know? Hopefully in our lifetimes we get to know.
Which leads to another question from Trevor Barry. The forms of energy we are familiar with are determined by their wavelengths. What wavelength might dark energy have?
Yes, a great question. So this is where it gets tricky, because when we talk about energy densities and things like that, we do attribute our energy with wavelength and frequency. However, that is only true for our electromagnetic energy that we can measure and use, and we don't think that dark energy is on that same scale or spectrum. So we don't think there's a wavelength associated with the dark energy, rather just a constant pressure. It's really tough to try understand how a constant exists in the universe and why a constant exists in the universe. So there's another big question. I didn't touch on it today, but there's a question about alpha. You might have heard of the constant alpha. I am by no means an expert at all in understanding this, but we want to understand, does alpha change? And if alpha changes, then it means that pretty much all of our constants end up changing with different parameters. But alpha itself, we think, is just a property of the universe, just some number that the universe likes to go to in certain situations. This type of physics really, it hurts my brain in the best possible way, because it's really trying to understand and almost accept, which is difficult to do, is that there's a heap of these hidden rules in the universe, hidden physics that dictate the way our universe is. So, for example, the fact that our atoms are even clumped together, we have to thank the strong and the weak nuclear forces for that. Without them, the atoms would never clump together, or they would never clump apart. So we think that dark energy is kind of one of those hidden secrets where it just is, but we don't know for sure, because it's very difficult for us to try figure out a way to do experiments to confirm things, because it acts on such large scales that we would never be able to detect its effects locally here on Earth or even in our galaxy, because it acts on enormous amounts of scale that it's moving. So I'm sorry, that was probably not very helpful.
No, that's an excellent response. Thank you. And just another question from David O'Driscoll. Do you think recent questions about the standard model may lead to a better understanding of dark matter?
Yeah, so I think this might be around some of the our measurements of trying to measure different, like, W bosons and things like that, because there's a whole heap of things in particle physics. Again, particle physics scares my pants off with how complicated it is. But using things like the Large Hadron Collider, we're able to then try forcefully make situations where we know certain particles should exist and should interact. And we're trying to do that to be able to measure different properties of particles. So particles are incredibly cheeky. So you've probably heard of wave-particle duality. This is when we talk about light. Light can act as a wave and act as a particle. And with light, that makes some sense. We can do experiments and confirm that. We also think this is true, though, for our small subatomic particles. And with this comes something called the Heisenberg uncertainty principle, that basically states that if you want to look at something, you can then no longer get X amount of information, because by observing something, you are basically observing it out of the state that it was in. And so there's a lot of experiments trying to forcefully observe certain smaller subatomic particles to try better understand what are their spin properties. There's something called color and charge, and things like that. And so I think a lot of these really cool experiments that are happening at CERN might just open up this door for being able to better understand, maybe this is an avenue of where we could try and look for dark matter. If it is part of our standard model, how can we produce it? Because to date, we haven't been able to forcefully produce dark matter. We can forcefully produce antimatter, easy. Dark matter, not so much. I think that's a very reasonable thing that we might be able to expect, is either it will open up our understanding to find a way to pop it in with our standard model, or it will give us more door closers to then maybe say, it's maybe not part of our standard model at all, and then that can take us in another direction of, is it something that we can observe then?
Starting to get some questions coming in right at the very end. So from John Waugh, could dark matter relate to Higgs boson? If the Higgs boson only gives mass but doesn't interact with anything else, is there some relationship?
Yeah, that's a great question. So we think that we know that the Higgs field, or the Higgs boson, is able to help give mass to those subatomic element particles, and then basically give things their mass so then they can interact and clump together. I think we are still very unsure of if that Higgs field, so the field that you have to interact with to get your mass, if that relates to dark matter. So I think some of the thinking is that if it's part of our standard model, and maybe it is made out of something that isn't a baryon, isn't a fermion, but is somehow related to those things, possibly, or if it's a different realm house altogether, if it could have its own field that it interacts with. So instead of it being a Higgs field, it could be, the mystery field that helps give it its matter. It's very tricky, because when we chat about our type of matter, we know that we have spontaneous particles popping in and out of existence all the time. We tend to call them virtual particles, but it's basically that the universe is, you can think of it as like a hot soup of quantum fields that are constantly interacting and jiggling around, and every now and again they can wiggle in a way that pops particles into existence. It's always a particle and an antiparticle, so they annihilate each other, fall out of existence, but that happens continually. But we're not sure if that happens with dark matter, and what that might mean. We're not even sure if dark matter if it is a particle, then theoretically it should have an antiparticle. Lots of really, really good questions, and really it's complicated to try to put into what we know about the universe, because we think we know a lot. I mean, I if you look at our textbooks now compared to a couple hundred years ago, oh my goodness, we're geniuses. But what are the people going to say in a few hundred years when they look back at us? They're going to be like, oh, they knew so little. I think it's really difficult to know what we don't know, but at least we know that we don't know it. So that's a good thing.
There's another question here from Julie Rogers. Thank you, Sara, for the great talk. Could you please comment on the recent theoretical work attributing dark matter to gravitons acting in higher dimensions?
I'm unfamiliar with this, but it might be related to string theory modeling, possibly. So I don't know if it is, but from my understanding of, so we can model what our universe might look like instead of being particles or waves, they're harmonic strings, so our string theory. But for this to work, we have to add dimension on dimension for it to all work out, and then us get this 3-4-dimensional universe we live in. So I would definitely have to do some reading on that, but it could be related to this modeling of what if everything is not a particle, but rather a harmonic string. So I can't comment on it quite yet, but it would be interesting to have a read, because there's always that possibility that we understand our universe very well in the 4 dimensions, so 3D space and then time, but is that all that we're limited to? Who knows? I love a bit of sci-fi, so I always love the idea of higher dimensions, lower dimensions, and I think it's something that it's really tricky for us to figure out how do we even detect things like that.
Just a couple more questions for you. One from Trevor Barry. So could dark energy be considered more akin to gravity as force?
Yeah, you could kind of think of it as that way. So we think of, so really gravity is just space-time bending, and we can think of dark energy as just space-time stretching. So space-time itself, if you had an empty fabric, a square of space and time, you could put mass on it and bend it and create gravity. But if we're talking in dark energy sense, that fabric would just inherently want to stretch. It wants to push away. So it's similar but different. So it's just something that the space and time wants to do. So just like it can bend for matter, it wants to push, just because it must be a bit angsty. It wants to push away.
And I think I'll make this the last one. Finally, from Ian Enting. Does any of this relate to discrepancies in estimates of the Hubble constant?
It does. Great question, Ian. So dark energy a lot is what we use, or modeling of general relativity, which involves our modeling of what we call the lambda CDM. So when we break down, if we're trying to write a recipe out for our universe, we have all of the matter we know, we have dark energy, and we have dark matter. And we use what we think dark energy and dark matter are. So for dark matter, we think that it's cold, we think that it's weakly interacting, and for dark energy, we think that it's constant. And so we use all of those in mathematical terms to try solve Einstein's field equations. And we can do this, then we can figure out the Hubble constant or H naught over time. And what we're finding is that different ways of measuring H naught or Hubble constant at different periods of the universe, there's big discrepancies. So if you use the cosmic microwave background radiation, so the CMBR, which is the very first light emitted from our universe, you get a different Hubble constant to if you use supernovae to map the local universe by quite a few significant figures. I think it's about a 3 to 4 sigma tension at the moment. And so there's a lot of effort going into trying to consolidate. So we want to know, did the Hubble constant change from the beginning of the universe to now? Or is it that we're not getting the full picture of the universe now to be able to map it back to what we saw at the beginning of the universe? And so lots of work is going into better mapping distances to galaxies using things like supernovae and being able to calibrate them with different methods. So it's a really, really interesting topic, and hotly debated. If you go to I've only been to one cosmological conference in my life, but it was very fun watching people get very passionate about why H naught has to be the way it is, because it's a mystery. It's very cool, and a lot of good science that can be done with it.
All right. Well, thank you very much for that, Sarah. I really enjoyed it, and everyone else from the looks of it really enjoyed it as well. We're starting to get some people coming in from WA now, so that's nice to know. And
awesome.
Thank you very much for offering and for doing this presentation. It was really great.
Oh, you're very welcome. It was my absolute pleasure. And enjoy the rest of the conference, everyone. Thank you very much.
So that concludes today's session 1. Session 2 will start at 11 a.m. and you can find the link to that on the NACAA webpage as listed there through either YouTube or Facebook. So as I said, we'll be returning at about 11, and thank you very much for watching.